Hello, class. Today we are going to start a new topic. This is an important topic which lays the foundation for functional programming paradigm. And functional programming is a very important way of writing a code which leads to very robust and correct software in general. And most of the modern programming languages like Java, Python, even JavaScript, and almost any other language which is in use incorporate some form of functional programming principles in their languages. Okay. So to better appreciate all of these languages in their functional offerings, it is important to understand the mathematical or the theoretical foundations of functional programming. And this is important so you understand how the paradigm was transformed over the many years. You would notice that the Lambda Calculus, which happens to be the foundation, mathematical foundation, was invented in the 1930s, well before modern day computers were built. So over the time, over all these years, this has had a big impact on how good and correct and robust software is written. Okay? So that's the reason we study Lambda Calculus, and we will not get into too much of the depth of the Lambda Calculus, but we do want to understand the basics. All right? Okay. Just a little background. Of course, functional programming, the term function in a functional programming is important for all us to understand. And I think we have seen functions maybe even in high school, or certainly in the discrete math course we teach in our computer science curriculum. All right. Functions, mathematical functions, that is. So f of x equals x squared, for example, the square function. Okay. Now, there's a different way to look at functions as well as a computer scientist, and that is every computer program you write, okay, the whole program I'm talking about, the complete program, can be thought of as a function from some inputs to some outputs, right? So you write a big software for a few thousand lines of code, and then you run it or deploy it somewhere, okay? And it's going to take some input from some users at some places. Maybe the input is through a terminal, or it is through a mouse click, or maybe somebody is filling in some text boxes on a web application, or whatever it is. There is some input, or the input is being read from a file, text file, or maybe stream data coming from a stream or something, data stream. So there are inputs coming into this program, and there are outputs coming out. See. So whenever you have such a situation, you can visualize this or think of it as a function, mathematical function. Okay? And this question of what does it mean for a function to be computable, okay, now was a very important question in the early and mid 1900s. A lot of mathematicians who were thinking about computing posed this question, and in the early 1930s, answers came out to this, okay, or late 1920s and early 1930s, and three different answers came out of this one question. Okay, what does it mean for a function to be computable? Okay, what is computable in the sense we understand these days? Is it? That is, a computer program does some computation, right? So three, and I've pasted the three faces of the three famous people, okay, who came up with this answer to this question in three different ways, okay, from different thought patterns, and eventually it turned out that all the three ideas or all the three answers were essentially the same. You see, in the sense that they were all equivalent. Okay. We don't have to get into all of that detail for this class or for this set of slides. We're going to discuss the Lambda Calculus. Okay, but let's look at the three answers which came out of the thinkers, the heavy thinkers of the 1930s. Okay, Alonzo Church, who's shown on the left here. Okay, He was a professor at Princeton, I believe. Okay, and he came up with a solution called Lambda Calculus. Okay, or answer to the question what is computable. Okay, and he proved that, or he stated that he claimed, rather than a proof, he claimed that a function is computable if and only if it can be written as a lambda term in his calculus. Okay, lambda calculus. And this is the topic we are going to study in the next set of videos here. Okay. At the same time, Alan Turing, of course, he's more famous than the other two names, especially to the computer scientists. Alan Turing devised something called a Turing machine. Okay, and he said that any function which is computable, we can say it is computable if and only if it can be computed using a Turing machine. Okay. All right. So lambda calculus was one way to define what is computable. Turing machine was another way to define what is computable. And actually, a little while earlier, ahead of Church and Turing, Kurt Gödel, he was working on looking at the same problem, but much more mathematical, even though the other two methods are also mathematical. But recursive function theory is a theory which was being developed even before Church and Turing came up with their ideas. Okay, and Kurt Gödel was the prime driver of that theory, okay, recursive function theory. And he claimed that a function is computable if and only if it is general recursive. That's a technical term inside the recursive function theory. Okay, it's a very interesting mathematical theory, recursive function theory. I mean, if you get a chance, at least read up the Wikipedia page, if nothing else. Okay, so at least you get an appreciation for that mathematical theory, which defines what is when a function is computable. Okay. Anyway, there are these three subjects or three answers to that question, and of these three, all three are relevant to computing because all three define what is computing, right? In some sense, but lambda calculus and Turing machines, both those methods have even more practical implications in computing. Okay, and that's the reason why it's important for computer science students to at least know the basics of lambda calculus and also learn what a Turing machine is and how that works. Okay, if you do take the automata class, which we teach in our department, we do cover Turing machines in detail in that subject. Okay. So anyway, there were three different answers by three different people. Of course, they were all talking to each other. I believe Turing was a student of Church at Princeton at some point in time, okay, or around the same time. So they had robust discussions, I'm sure, amongst them. Anyway, so that's all we will talk about as far as the main question, which was importantly posed in the early part of 20th century, that is to say. And these heavy thinkers of mathematics and computing came up with the answers, and lambda calculus and Turing machines have much more practical impact in the development of the field of computing. Okay. All right. So let's go focus and zoom into lambda calculus. Okay. This is just some observations at the higher level and also its impact. Okay. Lambda calculus is a mathematical formulation. It has a very simple syntax and also very simplistic semantics, the meaning of the syntax, that is, okay. And it's actually an excellent vehicle to study the meaning of programming languages, not just functional, but even others, you see. So that's one of the reasons, because of its simplicity. You can use it to understand the meaning of programming languages, okay. The second point is that over the years, especially in the recent years, there's been a stream of functional programming languages which have been proposed, purely functional programming languages, but also other languages have incorporated functional programming paradigm within their definitions. You see? So, example, popular languages are Haskell, Lisp, a little bit older, 1960s, 50s and 60s, Scheme, which is a variation of Lisp. These are some of the popular languages which follow the functional programming paradigm. And all these languages are syntactic variations of the lambda calculus. Okay, So at the heart of it, the features of lambda calculus are implemented in Haskell, in Lisp, in Scheme, and so on. Okay, so which means that if you want to understand meaning of Haskell programs or Lisp programs, you can actually use the semantics of lambda calculus in understanding the meaning of those programs there. Okay, and the third point is something we will actually cover a little bit in this class as well, or actually we might have covered earlier. With these videos, not sure which comes first, which comes later, but I believe in the first part of the course we cover denotational semantics, a way to provide meaning of programming languages, and that actually grew out of lambda calculus. So you can actually see lambda calculus has had a big impact on the development of programming languages and semantics and so on. Okay, so this slide is important in the sense that it conveys the fact that lambda calculus has had a big impact. Okay, and understanding the basics of lambda calculus is important for every computer scientist. Right? I hear sometimes students say, "What is this? Why are we learning this? We're never going to use it," and so on. But you will see that when we move forward, you get a better appreciation for functional programming. Okay, all right. Now let's just do a brief recap of functions. We have learned functions probably since high school. Okay, functions on numbers is what we usually do in high school and so on. Okay, only when you come into pure computer science we start talking about functions on strings and other things. Okay, and more general purpose functions. Okay, so. In this slide, we are going to talk about three different observations about functions, which we are familiar with. Okay, and these three observations form the basis for the lambda calculus. So that's why these three are being discussed here. Okay, the first is that you don't have to give every function a name. Okay, I mean you could. It's nice to give it a name, but it's not necessary. Okay, the function name is just an easy reference to the function, okay, but the function, the syntax and the content of the function can be described by describing the input parameters and the output which is being produced. Okay, so that's really more important when you define a function, the input and the output, rather than a name given to that particular function. Okay, so here in the first example here, okay. Let's see if I can use my this thing. Red color is fine. Okay. Yeah. So here's a function which is written in a particular notation. Okay, and we may use this notation subsequently as well. Okay. There's an arrow or equal greater sign in the middle. Okay, that separates the inputs from the outputs. Okay. To the left of it is the input. Okay. And to the right of it is the output. So x is just a name of a variable. Okay, so x is you can think of it as the parameter. Okay, the parameter for the function. Okay, and the output is x times x. Okay, which is x squared. Okay, this is a pretty common function. All of us have probably used it sometime or the other. Okay, for example, if the number x is 3, then the output is 9. 3 times 3. If x is 5, the output is 25. So this function everybody understands. Okay, we didn't give it a name. We have just described its content. Okay, the content includes input parameters and output. Okay, so in this case, the input is x, output is a formula, mathematical formula, x times x. Okay, so that's the first observation. Functions need not be named. Of course, if you wanted to give it a name, you could have. Okay, let me see if I can quickly bring up. Maybe a terminal. That's I like terminals. Okay. Okay. Maybe I should disable the pen here and then bring up the terminal here. It was starting to write on the terminal. Okay. I'm just pulling up some file, text file. Okay. So this function x arrow x square doesn't have a name, but if you had to build it in let's say Python, you would say something like this, right? Def square x and return x times x, right? So that's how you define the function in Python. Okay, got it? So the name there was the square. Okay, so that was the name. Okay, and x is the parameter here, you can see, and the output is x times x. Okay, here x times x is the output. Okay, so you can actually see that there's a lot of syntax around the functions. For example, the keyword def. Okay, that's just to indicate that this where the function begins, or the function definition begins. Okay, and square is the name of the function, and then within parentheses we put the parameter x. So you can see that the def, the square, the left and the right parentheses, and then the colon. These are all syntactic symbols which are really not very critical in defining the function, right? The essence of the function is really the x is the input and x squared is the output. Okay, even the return keyword is really not part of the essence of the function. Okay, so if you really extract out the essence of this function, that's what you see here. Okay, without a name. Okay, so that's the first observation. The second observation is the choice of the name of the parameter is irrelevant. Okay, that is we call the parameter x here, correct? That's just an arbitrary name for the parameter, and that you are also familiar when you write Python functions or Java methods and so on. You choose the name of your parameter, right? Nobody forces you to use one name or the other. Okay, you just choose. Okay, and it's irrelevant. You could have called it x, you could have called it y, and that's what the second point is illustrating. So x arrow x times x and y arrow y times y, both these are the same function. Okay, both of them take one input and then return the square of the output, square of the input as the output. Okay, so the name of the parameter is not critical. Okay, or irrelevant is what we are saying here. Okay, functions need not be named. The choice of the name of the function parameter is irrelevant as far as the function is concerned. Right, both of them are the same function. Okay, and the third point is a little bit not intuitive, okay, especially to computer scientists, okay, and that is that suppose you had a function which takes two parameters, okay, x and y, okay. Now in Lambda Calculus you might write it this way. Now technically you're not allowed to write it this way, but let's think of it, okay, in parentheses x comma y, so those are the parameters before the arrow here, okay, and then let's say the output is x plus y, so the sum of the two inputs, okay, so that's a function. Now we will soon see that functions in Lambda Calculus must be written with exactly one parameter. Okay, so that's sort of a constraint, and that seems unintuitive to computer scientists. Okay, why restrict to one function, one parameter? Okay, but there is a nice, neat trick in calculus, in Lambda Calculus, which allows you to go with this restriction and not reduce the power of this language, okay, or power of this formalism, okay. And this method of just restricting to one parameter is referred to as curry, okay, currying. We'll see this later, okay. Haskell Curry was the name of a famous mathematician. By the way, he's the one who's been honored in the Haskell programming language, okay. It is named after him. And he invented this mechanism, okay, or he became famous for propagating this mechanism of just converting many parameters into one parameter, okay. So, and this is how we do it, okay. So we actually sort of chain these parameters into a chain of functions, okay. So we take x, the first parameter here, and say that's the input, okay, and the output is a function. Okay, so this is a little bit unintuitive. Previously, the output was x times x or x plus y. Those are just arithmetic expressions which give you the value, okay, like a number, okay, numeric value. But now you're seeing that x is the input in this last function here, x arrow, x is the input, but the output is actually, you can see that it looks like a function. It also has an arrow with the left and the right side, right, within parentheses. So the output is a function. So this is something you have to get used to in functional programming, and it's one of the core principles of functional programming, and that is function values, okay, are also first-class values. That is, they're treated like numbers and strings and so on. Functions themselves are treated like that. Okay, so you can have a function constant, you see, for example. Okay, so in this case, the input is x, the output is a function which takes an input y, and the output is x plus y. Okay, and that function, the y arrow x plus y, is defined in the context of the outer function. So that's why we can access the x parameter which comes from the other one. Okay, so this is a nice trick of chaining one function to another function, or many. In this case, there were two parameters, so we chained the two x and y. But you can go x, y, z any number of times, and eventually at the end you'll probably return the expression which you want to. Okay. So this mechanism is, we'll get used to it. Don't worry about it. Okay, we'll have many examples like this for the in this class. Okay. So there are these three observations. Functions need not be named, unnamed functions, that is. Okay. Second is that the function's parameter name need not be a particular name. Okay, it's irrelevant. You can choose any name you want. Okay, and the third is that functions must have exactly one parameter. Okay, this is a little counterintuitive to what we've been used to in programming, but in functional programming you can actually do this. Okay, and this is actually one of the core features of functional programming. So that's why functional programming is so powerful, because of this feature, the third one. Okay. Anyway, so those are the three observations of functions. Okay, and those three observations you'll see in the formal syntax and semantics. Okay, in a couple of slides we're going to get to that. Okay, but let's look at one more example here. Okay, cube. Okay, so here's another function. Okay, I'm writing it a little differently here. Okay, doesn't matter. Okay, so this is the name given to that function. Okay, cube. Okay. Colon, okay, colon, and to the right of that colon we have a signature. Okay, so this is written in a little different format. Okay, you might be familiar with this if you have done some function programming, or even in some mathematics also we describe functions this way. Okay, so the signature or the domain and the range. Okay, yeah, that's right. So you remember domain and range. So integer, this integer is the domain, and this integer is the range of the function called cube. Okay, got it? So that's the notation being used here. And here in the next line we are describing what the cube of n does. Okay, if n was an integer from the domain, then cube of n, in this case we are defining it as n cube, is also an integer, right, from the range. Okay, so that's the function. Okay, so this is a mathematical function we are familiar with. Okay, so now let's ask some questions. Okay, so and assuming that this is part of a programming language and cube has become a variable. Okay, like int x, you're defining cube as a variable. Okay, and the data type of cube is this. Okay, this part here, that's the data type. Integer arrow integer. Okay, that's how you describe the data type of a function. Okay, so cube is a variable, and so the question is, what is the value of the identifier or variable cube? Okay, that's an interesting question to ask. It's almost like asking, going back to the Python example there. Okay, this one here. Okay, so what is the value of square? Okay, square is an identifier in Python, right? In this particular program. So what is the value of square? Okay, now if you had said x equals 5, or let's say z equals 5, okay, in Python, okay, and then if I asked you what is the value of z, then you would say 5, correct? Z is an integer variable, or in Java you would probably do it like this, int z equals 5, right? Something like that. So in Java, int z equals 5, if I ask you what is the value of z, you would say, yeah, z is an integer variable and its value is 5, okay? But if I ask you the same thing of square and ask you what is the value of square, you probably know what it means, but I think we're not used to talking about values of functions, right? And that's the point here, okay? The point is that in functional programming, if you do give a name to the function variable, the name, okay, also has a value. Okay, and that's what is behind this question: what is the value of the identifier cube? Okay, and what will be the object which will be bound to cube? Okay, in this case, it is the n cube, right? Or even the signature int arrow int, and then the body of the function, which is n cube. Okay, right? So the cube. So there will probably be an object internally. Okay, in function programming, these are called function objects. Okay, which will hold the signature. Okay, signature is really the data types of the inputs and the data type of the output. Also, the object will hold the code which goes into the body of the function, right? So that code itself becomes part of the object. Okay, so that's really what we mean by what is a object bound to the variable cube here. Okay, and the third question is, can we define this function cube without a name, just like for example, going back to this integer z. Okay. Integer z equals 5, okay, but somewhere else we can say z equals z plus 12, right, in your program. So in this case, the number 12 is a literal, right? It's a constant literal, it's a numeric literal, okay? So we didn't give it a name, right? So we didn't give it 12 a name, right? I mean, it'll be really too much to ask all programmers to say int 12 equals 12 and then force the users to say z equals z plus 12. Okay, sorry, this 12. I mean, this would be torture, right? If you're forced to give a name to every constant you write in your Python or your Java program, and nobody's going to use that programming language, right? Aren't we glad that we're not forced to do that? Okay, so that's really the point here is even the function literal. Okay, function also you should be able to give it a value without giving it a name. Okay, like the 12. Okay, so that's the point here. So these 3 points again illustrate the same 3 points we discussed last time. Okay, in a different way. Okay, and finally here is how. Oops, excuse me. Yeah, let's see if I can show you. Yeah, I think it's this one here. This is good. I like that. So that this thing is carried over from the last page. Okay, I want to circle this and show you. Okay, what this says is that this is the notation we're going to learn this obviously in Lambda Calculus for this particular function without giving it a name. Okay, lambda. Okay, lambda is just a syntactic symbol. Okay, and then the n sitting next to it is a parameter, the single parameter, and the dot separates the parameter from the body, and the body is n cube. Okay, so this is how you write it in Lambda Calculus. Okay, and this is a function which is anonymous, so it doesn't have a name. Okay, right? Okay, let's continue. Okay. By the way, I like to make videos of between 30 and 35 minutes and then give a break. So let's see whether we can cover a few more slides. Okay, we are at the 28-minute mark. Okay, all right. So again, continuing with the concepts, let's look at a different function. This time it is the 2-parameter function. Okay, again, this is in the mathematical notation here. F is a function. Okay. And its signature is the inputs and the output, domain and range. In this case, the domain is a Cartesian product, okay, or you can think of it as two inputs, okay, integer and integer as two inputs, and the output is an integer. And the function's definition is f of m comma n equals n squared plus m. Okay, so that's a function n squared plus m. Okay, it squares the first input and then takes the second input and adds the n squared and m. Okay, and that's the return value. Now, since Lambda Calculus, we already indicated, does not allow functions with more than one parameter, that is, functions must have exactly one parameter, f would be represented in this manner. Okay, this particular f would be represented in this manner. Oh, again, maybe going back to the, let's see, I do have an eraser here quickly. Okay, this one here. Okay. All right. Now this function would be written this way: f of mn, m comma n equals n squared plus m. Okay, since there are two parameters, we had to string them. Okay, remember the currying concept we learned, we discussed last time. So lambda m dot lambda n. So we are saying that lambda m is the first parameter into this function, and then the output of this function is a function which is lambda n dot n squared plus m. Okay, so you sort of separate the two parameters into two lambdas, and then in the body of the inner function you say n squared plus m. Okay, and you can access m inside there. Okay, so that's how you would represent this particular function. Okay, n squared plus m in lambda calculus. Okay. In the other notation we discussed earlier, it will be written as follows: m arrow, n squared plus m, almost the same. So you can see a lot of similarities between the lambda notation we are starting to introduce here and the other notation, or more mathematical notation we discussed before. Okay, all right. So that's just some overview of some functions and so on. Okay, functions, mathematical functions. We have looked at mathematical functions so far. Okay. And now we are ready to define the syntax. Okay, so this is the first formal definition within lambda calculus. Okay, it's an important slide because it defines the exact syntax. Okay, so I'm using the PDF highlighter here. Okay, so what we're defining is a lambda term. Okay, that's a very technical term. Okay, a lambda term is the syntax that you can think of lambda term as a program. Okay, as a computer program or whatever. Okay, so a lambda term in lambda calculus is defined as follows. Okay, it's a recursive or inductive definition. Okay, the first part of the definition is that you are allowed to use variables. Okay, x, y, z, m, n, p, whatever, any name you can choose. Okay, a variable itself is a lambda term. Okay, so that's a building block. Okay, the simplest type of lambda term you can make is just a variable name. Okay, x or y. Okay, and then there are two mechanisms of building bigger lambda terms from simpler lambda terms. Okay. Okay. The second one is built as follows: left parenthesis lambda x dot m right parenthesis. Okay, so you can note the parenthesis before and after. Okay, so the parenthesis would indicate that it's a beginning and end of the term. Okay, and within that begin and end we have a lambda x dot m. What is x? X is a variable. Okay, which will be treated as a parameter. Okay, parameter variable. Okay, and what is m? M is a lambda term. Okay, what lambda term? It could be anything. Okay, it could be anything which is constructed with this definition. Okay, so that's a recursive part. You see, the m is a lambda term. Notice that we are defining lambda term and we are using lambda term. That's what makes this definition a recursive definition. Okay. And the third part is another way of defining a lambda term, parenthesis, again enclosed within parenthesis, m and n with a space between the two. Okay, and what is m and what is n? They're also lambda terms, so you can make a bigger lambda term by putting two lambda terms next to each other and putting parentheses around the whole thing. Okay, so that's all. So this is the complete syntax of lambda calculus, which Church wrote in his paper way back in 1930. Okay. And imagine just these 4 lines defines what computing is. Okay, that's really incredible. Okay, we'll come back to the whole concept much later. Okay, or while we study lambda calculus. But let's look at the purpose of 2 and 3. Okay, the purpose of 2 is is to define a function. So this is how you define a function. Lambda x dot m is how you define a function in lambda calculus. Okay, and m and parentheses is how you call a function. Okay, so just defining a function is not good enough. You have to have the ability to call it, right? Only then the computation takes place, right? If you don't call a function, nothing is going to happen. Okay, so the number 3 is how you call a function. You place hopefully a function m, and then n is the actual argument to that function. Okay, so you can imagine if lambda x dot m was a function, then this x will be replaced by the n. Okay, That's so you're actually calling the function with n, okay, where m is the function, okay. So these are called the lambda abstraction and lambda, function application, okay. So m here is called the rator, okay, R-A-T-O-R sometimes, okay. Operator, it comes from the word operator because that's the operator, and operand is n, okay, that's what you provide as input, right? So this is called the rand. So this is the rator and the rand, okay. That's the terminology, okay. And also in the lambda abstraction, x is the input parameter. It's also referred to as the bound variable, okay. And m is the body of this function, body, okay. All right, we're going to stop here. This is 35 minutes, and we'll come back, we'll come back to this next slide and then continue from here in the next video.